accept that carbon dioxide is a greenhouse gas. That means that carbon dioxide molecules absorb radiations coming from the Earth. Which begs the question, why do they? Especially in the context of the fact that many other substances, including the nitrogen and oxygen in the air, do not absorb those radiations. And carbon dioxide doesn't absorb radiations of other wavelengths other than those being emitted from the Earth. So why do carbon dioxide molecules absorb those particular radiations? Is it because of some characteristic of carbon dioxide molecules that means that happens? Or is it because of some characteristic of the radiations? Well, let's have a look. First of all, what about the radiations? Any object that radiates heat, energy into a vacuum, the wavelength of the radiations or the energy of the photons of those radiations depends only on the temperature of the surface of the object, not what it's made of. So whether it's the sun or the earth or a cup of tea or whatever, it's only the temperature that decides what the energies of the radiations are. In the case of planet Earth, its surface temperatures are such that the radiations that it's emitting towards space are in what's called the long wave infrared regions of the electromagnetic spectrum. Electromagnetic spectrum, here we have the whole range from gamma rays up to radio waves, from very, 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 very short and high frequency and high energy, up to very, very long wavelength, low energy photons, the radio waves. In all of that range, gamma rays, X-rays, ultraviolet, infrared, microwaves, radio waves, visible from blue to red, is in this small section of the total electromagnetic spectrum. And out here, just a little bit less energetic photons, slightly longer wavelength is the infrared, and towards one side of that is the long infrared, and it's in this region that the radiations emitted by Earth at its temperature of 15 or so degrees emits radiations. Okay, so that's the characteristics that we need to know about the radiation. What about carbon dioxide molecules? I'm going to come towards a simplified explanation here, but I hope enough for our purposes. And carbon dioxide absorbs a photon of radiation that, coming from the surface of the Earth, it gains some energy. And where does the energy go? It results in faster vibrations of the atoms in the molecule. It jiggles faster. Now, the key to the whole story is that the energy of vibration of molecules, all molecules, including carbon dioxide, is that the energy levels are quantized. And that means, we've talked about this in another context, the molecules can only vibrate with particular levels of energy. They cannot vibrate with energies that are different from the allowed levels. And that will seem probably quite strange to our experience, because we can walk at any old speed we want to, we can drive at any old speed we want to, but molecules can't vibrate at any old speed they want to. There's a portrayal of energy levels, 1, 2, 3, 4, equally spaced energy levels. And the idea of quantization is that the energy of vibration of a carbon dioxide molecule can only be, if we're plotting more and higher energy in the vertical axis, can only have that value, or that value, or that value, or that value. but it may not have any value of energy in between. We say they're not allowed, but not allowed in the sense of someone who's saying you mustn't do that. They're just not possible. Now that has an enormous consequence, that if a molecule that's in this level is going to absorb a photon, it cannot absorb a photon which would take it from there to there. It's not an allowed condition. Or from there to there. Or from there to there. Or from there to there. There cannot be a transition, as we call it, an excitation of the vibration of the molecule to a level that is not allowed. So there are only certain transitions that are possible. And here, for example, an allowed transition is from vibrational level of energy 1 to vibrational energy 2, exactly. Or from 1 to 3, or 2 to 3, or 2 to 4, or whatever. We can't have one that goes only partly towards 2, or between 2 and 3, or between 3 and 4. That would lead to the formation of a vibrational state which does not exist, is not allowed. So, dum-da-da-dum-da-da-dum, the energies of photons of radiation emitted from the surface of the Earth happen to be equal to the gap, to the space between allowed energy levels of vibration. If we go back, carbon dioxide molecules are such that the gap between their vibrational energy levels 1 and 2 is exactly the same as the energies of the photons being emitted from space. And so carbon dioxide molecules can absorb those photons and will take it to that particular level of excitation. You remember the second part of the story is that shortly after that they will de-excite again, and a photon will be irradiated in all sorts of random directions. But there is the answer. So they can be absorbed because it's an exact match, and indeed they are absorbed. Here's what we call a vibrational spectrum in the infrared for carbon dioxide gas. And the main one that we're talking about is this. This one corresponds the energy of the photons in this. It's expressed in wavelengths of the waveform, but for every waveform there's a corresponding energy of photon, and the energy of the photon corresponds with this level, and that's what's absorbed, because absorption there will take it to exactly the next level. So carbon dioxide absorbs radiation with wavelength about 4,300 nanometers. That's in here. At this wavelength, the energy of absorbed photons is equal to the gap between the allowed energy levels. And to go back here, radiations whose wavelengths or whose energy of photons are like this, or this, or this, or this, would take them to some intermediate level between allowed energy levels. And so those excited states don't exist, and so carbon dioxide does not absorb radiations of those wavelengths or those photon energies. It will only absorb there. Sorry. So I started off asking, why do carbon dioxide molecules absorb radiations? Is it because of something about the carbon dioxide molecules? Is it something about the radiations? Well, in fact, it's because there is a coincidental match, an exact match between the photons' energies and the size of the gap between the equal-spaced vibrational allowed energy levels. Who's decided that? Let me suggest it's Mother Nature. There are other molecules that do not absorb infrared radiations. Carbon dioxide does not absorb some other radiations other than these ones, because that match is not there. Aussie. Well, there's a couple of things puzzling me a bit, Prof. First of all, if there's an absorption of photons only from one allowed level to the other, and all of the allowed levels are equally spaced, shouldn't there be just one energy that photons can have that are absorbed? Every photon have exactly the same energy. And so on your spectrum, as you called it, there should be just one sharp line indicating absorption at that energy. But in fact, there seems to be a sort of a range of energies. Yeah. Good. Well, first of all, I won't go too deeply into this, but I did say I was going to do a simplified version. I talked only about the energy that the vibrations could have. Now, complication is that for every vibrational level, not only the vibrational levels quantized can only have certain levels, but rotation of molecules spinning over is also quantized. The gap between the energy levels of rotation is very, very much smaller than those between vibration. And there's a set of rotational energy levels for every vibrational level. So for vibration level energy level 1, there's a rotational energy 1, rotational energy 2, rotational energy 3, rotational energy 4, and for vibrational energy 2, there's rotational energy 1, rotational energy 2, rotational energy 3, much, much closer together. And that means, in fact, that we can have allowed excitation or transitions from vibrational energy 1, rotational energy 0 to vibrational energy level 2 and rotational energy 0, or vibrational energy level 1 and 0 to 2 and the first rotational level, or from 1 and 0 to 2 and the third vibrational energy level, or from 1 and the second vibrational energy level to 2 and the first vibrational energy level. The net result is that there's a whole range of photon energies, all of which can be absorbed by excitation of the rotational energy as well as the vibrational energy. I don't think there's much point going further than that, but I hope that that's a satisfactory explanation for now. And the other what? And the other one is, why would there be more than one energy range where there is absorption? There seems to be 3 peaks on that spectrum for carbon dioxide instead of just the one. Why would that be? Well, again, part of my simplification. Molecules can vibrate in a number of ways. So, for example, you can have, if carbon dioxide, this is the carbon atom, and here's 2 oxygen atoms, I can have vibration like that. I can have vibration antisymmetric, we call it, like that. I can have vibration of bending like that. And each one of those levels has quantized energy levels, and the gaps are different. So in fact, this particular one is the result of transitions between quantized levels of antisymmetric vibration of carbon dioxide. This one is between transitions between bending excitation levels. The gaps are different, and so the photons that it selectively absorbs are different. I must confess I don't recall what this one is. What you won't see in there, for reasons that we'll come to later on, are transfer absorption due to excitation of symmetric stretching of the carbon dioxide molecule. And that's for the same reason that we don't have absorption here by nitrogen molecules or oxygen molecules, even though by far the dominant species in the air are nitrogen and oxygen. It's the carbon dioxide that selectively does it. Okay, Ozzy. Good. Yeah, well, we'll come to discussion of those different vibrational modes shortly. So it's this coincidental match between the energy of the photon and the gap that is an allowed transition difference of energies. Okay?